So far in our discussion of acids and bases, we have gone as far as defining them through different definitions, including Arrhenius, Bronsted-Lowry, and Lewis definitions. We've also talked very briefly about pH and POH scales and describing solutions as being acidic, basic, or neutral. Now, with our acids and bases, if we go back to our definitions, we're looking at whether it's complete dissociation or it's proton transfer. We're looking at the generation typically of ions in solution, which means we're dealing with electrolytes. Now, remember in discussions of electrolytes from previous chemistry courses that they can be described as being strong or weak. And that description of strong or weak is really a description of the degree of dissociation. So how much is that breaking apart or how much proton transfer is occurring? It's going to depend on the strength of attraction between our ions. Strong electrolytes or strong acids and bases are going to have complete dissociation. Species that are strong undergo complete dissociation because their ions have a stronger attraction to water than they have to each other. And so they're going to have this strong driving force to dissociate because they're very strongly attracted to water than the original compound bonds. Now, substances that are described as weak, they're going to undergo only partial dissociation. These substances are weak and undergo only partial dissociation because their ions are more attracted to each other than they are to water. Or another way we can think about it is that our original bonds are stronger than that bond to water will be. And so we're able to either reform our original material or it doesn't break apart very well. So the first thing we'll take a look at are acids. When it comes to acids, again, they can be strong or weak. As far as strong acids go, there are 6 and only 6 strong acids. These are going to include hydrochloric, hydrobromic, hydroiodic, perchloric, nitric, and sulfuric acids. These you need to know. If you memorize these 6 strong acids, everything else will be easy. So you've got 6 and only 6. These 6 acids undergo 100% dissociation, meaning that all of that original compound completely becomes ions. So we can take a look at the dissociation in water of nitric acid. So nitric acid was in that list of 6 strong acids. So we would have HNO3. We place it into water. It's an acid, so it's donating a hydrogen to the water molecule, forming hydronium and nitrate. We're using that single arrow. Remember, that single arrow is always indicating complete reaction, or in this case, complete dissociation. So that is indicating that all of that nitric acid is producing hydronium and nitrate. So if that's true, if I start with 0.1 molar of my HNO3, it's going to produce 0.1 molar of my hydronium and 0.1 molar of my nitrate, because all of that acid becomes those ions. So if you think about what we're just told, we're asked to explain why nitric acid is a strong acid. And so we've got this competition here. I've got hydrogen originally bonded to nitrate. So we're coming into contact to water. What we're going to find is that this is going to be strong because that H plus is going to be more attracted or have a stronger attraction to water than the original nitrate it was bonded to. Now, for that water to accept that hydrogen or for that nitrate to try to take the hydrogen back, they have to be bases. So in reality, what's happening here is that the water is a stronger base than the nitrate. It holds or accepts hydrogens better. As a result, this process isn't reversible. That nitrate is too weak to steal a hydrogen back off of that hydronium and reverse the reaction. And since that's the case, my nitrate stays completely dissociated. My water holds on to that hydrogen, keeping our hydronium around. Now, when it comes to our weak acids, all other acids are considered weak. So again, this is why we need to know those 6 strong acids. When we look at any acid that we're given, if it's one of those 6, it's a strong acid. If it's not one of the 6, it's weak. So all other acids are considered to be weak. Now, the dissociation of weak substances is reversible. Therefore, they're going to reach an equilibrium. So we can look at a generic reaction. We have some acid, HA, interacting with water, producing hydronium and our conjugate base. Now remember, anytime we have an equilibrium, it's described by a K expression. Here, because we're looking at the dissociation of water, this is going to be, the dissociation of an acid, this is going to be called a Ka. It is the acid dissociation constant. So we set up a K. All Ks are set up the same. K is going to be equal to the concentration of each of my products raised to their coefficients, so their coefficients are all 1, divided by my reactant. And remember that when we've got things like pure water, we're going to omit those from our K expression. So my Ka is equal to the concentration of my hydronium times the concentration of my conjugate base divided by the concentration of my original acid. Now, when we talked about Ks for chemical reactions, we said that K was going to indicate the extent of a reaction. And so when we talk about the extent of a reaction, we're talking about the amount of products formed compared to reactants left over. So if we're talking about a Ka for an acid, what do we think that Ka for that acid is indicating? Now we're talking about a dissociation. So if K is the extent of a reaction, and here we're looking at a dissociation, Ka is going to indicate the extent of dissociation. Now, dissociation indicates strength. So the extent or the degree of dissociation indicates strength. Ka indicates the extent of dissociation. So in turn, Ka indicates strength. So in terms of strength, the greater the percent dissociation, the stronger that substance is. So the larger our K value, that means we're going to have a greater percent dissociation, which is going to indicate a stronger acid. The smaller our K value is, the less dissociation we're getting, so we're going to get a lower percent dissociation, which would indicate a weaker acid. Now, strength is not dependent on concentration. So we can have a high concentration of our original substance. All that extent is determining is how much ions are we producing, and not necessarily concentration. So how much or what percentage of our original compound breaks apart into those ions. Now, we've also talked about proton transfer, so we need to be able to still write proton transfer equations, and now we want to be able to set up K expressions. So if I've got the weak acid HF, we want to write its proton transfer equation in water, representing its dissociation. So if I have HF in water, this is a weak acid, so since it's weak, we're going to use the double arrows. We're going to transfer hydrogen to the water, forming hydronium and F-. It's an acid, so again, it's represented by Ka. So Ka would equal the concentration of my hydronium times the concentration of my F- divided by my concentration of HF. Again, that water Water is always a liquid. It's a pure liquid. We're going to omit it from our K expression. So when we talk about our acids, the strength depends on attractions of cations and anions. So hydrochloric acid, for example, is a strong acid because the hydrogen it releases upon dissociation has a stronger attraction to water than it does to the chloride. Or if we think about it in terms of base, the water is a stronger base. It has a stronger ability to accept hydrogens than that chloride does. Since the chloride can't steal hydrogens back from water or from hydronium, it's not going to be able to reverse the reaction, so it's going to stay dissociated. But if we look at something like acetic acid is a weak acid because the hydrogen it releases upon dissociation has a stronger attraction to the acetate ion than it has for water. There is some attraction to water, so we're going to get some dissociation, but the acetate is a strong enough base that it can also take some hydrogens back and reverse our reaction. So anytime we have dissociation, remember we get pairs. We get our two conjugate acid-base pairs. Both the base and the conjugate base are going to compete for hydrogen. The stronger base wins. So we put an acid into water, water's the base, the acid releases a conjugate base, they compete. If water's stronger, it stays dissociated. If the conjugate base is stronger, we're going to get that weak acid. So the stronger an acid is, the weaker its conjugate base. That's what makes it be a strong acid, because that conjugate base can't reverse the reaction. The stronger a base is, the weaker its conjugate acid will be. And in turn, the weaker an acid, the stronger its conjugate is. Now, strength of an acid is going to be dependent on molecular structure. The structure of a molecule governs if it is strong or weak. Strength is determined by the bond strength as well as bond polarity. Weaker bonds will result in stronger acids. If we think about why, to be a strong acid, we have to get dissociation. We need bonds to break. So the more easily those bonds break, the more of them we can break, the greater dissociation we get. So a weaker bond breaks more easily, allowing for greater dissociation. Now, additionally, the more polar a bond is, the stronger an acid is. So weak bonds, polar bonds give us stronger acids. Now, if we think about our polar bonds, we're asked here why is that going to result in a stronger acid? Well, what happens when we get very strong polar bonds? They become weak, particularly when we're looking at the bonds to hydrogen. As that very electronegative atom pulls electrons away from hydrogen, that hydrogen is going to be seeking out more electrons. That means it's going to break very easily. So polar bonds are weaker bonds. So in our next video, we will explore looking at different molecular structures and seeing how weaker bonds lead to stronger acids and ranking their strengths, as well as looking at bond polarities to determine strengths.